Dr. Memari again. The experiment we are covering today is about electrochemistry. Electrochemistry, based on the name, it involves electricity and involves chemical reaction. For this experiment, when you look at the lab manual, you review the lab manual, we have two types of approach or two types of experiments that we could do. One using galvanic cell. In a galvanic cell, the chemical reaction is spontaneous, is based on oxidation induction type reaction. One element is being oxidized, one is being reduced. The transfer of electron from the element being oxidized or loses electron, and then it would be transferred to the element that being reduced. It does generate electricity. For the electrolytic cell, the reactions that we have, these reactions are non-spontaneous reactions. So in this case, the reaction does not create electricity. What we do, we use electricity, we use the electrical energy to help the reaction to happen. The setup for the electrolytic cell is that we have this U-shaped glass tube. We are going to place the liquid to be analyzed inside this tube, the glass tube, and we have the cells, the graphites, using the clip. We are going to place in one side, one arm, and attach or connect to the battery, and the other one in another graphite cell or electrode in the other side, the other arm side. After we fill up the tube with the liquid, I'm going to add phenolphthalein to the solution. And the purpose of using phenolphthalein is that if water has been reduced, it's going to generate hydroxide ion, and it will show that reaction. It would be the evidence for reduction of the water. The first solution that to be analyzed is sodium chloride. So we are going to use a 2% sodium chloride solution to fill up the tube. And if I can please have the phenolphthalein. I'm going to bring it up, so if there is a color change, you could see it or it's more visible. One drop on each side is enough. And I'm going to place, it doesn't matter which one is cathode or which side is the electrode placed in for the cathode and anode. Based on the chemical reaction that is taking place, we can determine which side is cathode and which side is the anode. What happens in the cathode side is reduction, and oxidation happens in the anode side. To understand this experiment, I want you to go back. When you read the procedure, is not going to help much. So I want you to go back to the theory part and decide based on the what is being analyzed or what is being oxidized or reduced. Because in the theory part, I give you choices. You have choice of two elements to be reduced. Is either sodium gaining electron and being reduced, which gives you sodium metal. The other option would be water to be reduced, and the water would be, when it's reduced, it would generate hydroxide ion. If hydroxide ion is generated, the solution would turn pink color because we added phenolphthalein. So phenolphthalein indicates that hydroxide ion has been generated. That is the evidence for water being reduced. So hydroxide ion has been generated. Now, the choices that we had. So sodium is not reduced because we see that water is reduced and then sodium is not reduced. The water is either reduced or oxidized. So if water is reduced, then we don't have to be worried about testing if the water or evidence for water is being oxidized or not. It's because it's either reduced or oxidized in this case. What are the choices for oxidation? What can be oxidized here? We have two choices, which one is eliminated because we already know water is being reduced. Either water being oxidized to give H plus ion, which I should have like another indicator to show that H plus has been produced, or we could go with the process of elimination. We say water has been reduced, so we know that water is not being oxidized here. The other option for oxidation was chloride. Chloride being oxidized. If chloride is being oxidized, is going to produce chlorine gas. Chlorine gas smells strong and it has like a light yellow color. So I have to check for those evidences, and whichever comes first, I take it, and I will say that, yes, based on this evidence, now chlorine has been oxidized. So I know water has been reduced. I'm going to bring this closer, and in case if there is a color change, so we could see it at the same time together, we bring this closer, and I don't have to keep the electrodes in anymore. We're done with this part of the experiment. Now, the green color, the red color, thank you. The red color is obvious. That means that water has been reduced. And on the other side, there is a yellow color, a light yellow color that appeared. And that light yellow color shows that chloride ion has been oxidized. I could see it from here, that it's a light yellow color. You could look at the color difference. Maybe you could see it. The other evidence would be like the smell of the chlorine, and it does smell also that chlorine has been produced. So chloride ion has been oxidized to generate chlorine gas, and water has been reduced to generate hydroxide ion. I'm going to wash this tube or use a different tube to get started with the copper sulfate next. Okay, now I have the cupric sulfate, copper 2 sulfate in the U-shaped glass tube. I did wash it, but I'm going to rinse again the electrodes because I don't want to carry the chemicals from one reaction to another one. And I place the electrodes in each arm. Also, you want to add phenolphthalein. Phenolphthalein to each arm side. You will add the phenolphthalein and wait for reaction to take place. Now, similar to what we had before, water is going to either oxidize or reduce. If it does reduce, we get the hydroxide ion, the phenolphthalein would change color. If there is no change in color of phenolphthalein, then water is being oxidized, because that's a good thing. We can eliminate that, already have it out. Water is being either oxidized or reduced. So if it's not reduced, then we can choose that for the anode reaction. What are the choices here? For cathode reaction, where the reduction takes place, either the metal, which is the copper 2+, would gain electron and would change to copper 0. And copper 0 is a copper metal. Since the electrons are coming from through this the electrode, the graphite electrode here, and copper ions would grab that electrons and would be reduced, and they're not going to fall down, they would precipitate, or they would kind of stay attached to this electrode. So if we give enough time, and copper is being reduced, which we should see like red dots on that electrode, which we have to give time and we have to wait for it. And if the water is being, the other choice for reduction is water. If water is reduced, we will see the red color. If you remember from previous reaction, as soon as I connect to the battery, I start seeing the pink color, appearance of the pink color. So it shouldn't take that long for the pink color to appear. In this reaction, water is not being reduced because we don't have the pink color. I just have to wait and see the copper residue to collect enough copper for me to show you, especially through the camera. So I'm giving some time for this reaction to happen. Now that we have experienced already with one of the reactions, reduction happens on the right side. But why it's happening on this right side? Because the right side is connected to the negative side of the battery. If I show you this battery, I have the negative sign here with this, there's a different fitting here. So you could see the negative side, and this side is positive. So for the reduction, I should track this and come and check this electrode, take it out and bring it to you to compare the before and after color. This is the electrode before being exposed to the electrolysis, and this is the after. It's not going to be like very, very obvious. I'm going to also hold it to like a white background for you, but it's very visible to us, to me, right here. So if you look at this color change, so let me show it separately to you. The red color now is obvious. Now is obvious. If I bring this one here, this is black, and this one has like pinkish or copper color on it. Okay, so copper has been reduced, and we know water is not reduced because we did not see the pink color of phenolphthalein. So water is the only choice for oxidation at this point. Water has been oxidized because water is not reduced and copper is reduced. That's for the end of this reaction. Okay. Next solution, we have potassium iodide adding phenolphthalein. And the purpose of adding phenolphthalein is to see if water is being reduced. If water is being reduced, we get pink color appears in the cathode side. And now that we talked about the negative positive side and reduction took place on the right side, that's where we look for the red color. And if you notice, if you could see from the video, that the pink color is appearing right now, and this pink color is actually a pink color of the pink color of phenolphthalein, which in basic solution it turns to pink color. I will give more time just because I want like deeper pink color for you to be able to see it, but for me it's very obvious. So water, we had two choices for reduction. One, potassium can gain electron and change to potassium metal. It doesn't happen in this case because potassium doesn't reduce that easily. It's very reactive metal. And if we have a metal potassium or metal sodium in water, it would cause explosion, really. But it's a proof that the water is being reduced in this case. So water is being reduced and hydroxide ion has been produced, not the potassium ion. The choices for oxidation, we have iodide ion, I minus, that can be oxidized in the anode side, which is the left side. And when it does oxidize, it would give I2. I2 or iodine is yellow color, like yellow to brown color, and it would turn the anode side to the yellow color would appear in that side. The choices again for the anode side, for the oxidation, we have two choices. One is iodide ion to be oxidized to iodine. The other one is water to lose electron and produces hydrogen ion. Because we already have water being reduced, then I don't have to be worried about water being oxidized as well. But I also see that yellow color appear on the anode side. I'm going to bring this again closer, and we can see the close-up. So we can see the close-up here for the, okay, right here. You can see it in action, closer. See the pink color appeared on the cathode side. That means water has been reduced, pink color. And yellow color appeared on the anode side. The yellow color is an indication that iodide has been oxidized to iodine. So we have the yellow color and the pink color as evidence for a reaction. For the chemical reaction and for choices, please just go 2 pages back to the introduction part in the experiment and look for the choices. Those choices are given to you. And that's the end of this reaction. Okay, we tested the sodium chloride solution, cupric sulfate solution, potassium iodide solution. The last solution for this experiment, which is part B of the experiment for electrolysis, is the sodium bromide. By now, you have already should know the pattern. What do we expect? Metal can be reduced or water can be reduced. I added the sodium bromide. I added the phenol drops of phenolphthalein. I'm going to connect the graphite or the electrode, place it in the solution. If water is being reduced, we expect pink color to appear in the cathode side. And any side that pink color appears, we can call that cathode side because we know reduction is taking place because hydroxide ion has been produced. But based on the experiments that we had, we know the right side is the cathode side. So the two choices we have is either sodium being reduced or water being reduced. It's easier if the water reduced is much easier to see it, so we don't have to work too hard for that. It's already changing pink color, and pink color is kind of obvious, and I can bring this slightly closer. So we have this water is being reduced. So sodium is not being reduced. Now, on the other side, bromine is going to be oxidized. Bromide ion is going to be oxidized because the other choice that we have is water. So since water is being reduced, we don't have to be worried about water being oxidized. And so bromide is going to be reduced. When bromide reduces, it gives us like a yellow-green color, and is not as colorful as the iodine, but it sounds a little better than the chlorine. I'm just giving some time as I'm explaining. I'm giving some time for more bromine to produce, so I could show you. I could see that color right now, but I'm just trying to get a little more intense in the color of the solution to give time to get more intense color in the solution, so you can see it via the camera. So either I bring the camera closer or bring the tube out and using like white background here, and you see that the difference. Maybe I can bring this up so you could compare the color. It's very obvious to me right now. The green, yellow-green color fade like very light yellow-green color, has been produced. But for you, I want you to compare this. When I put the white background, I want you to compare this area of the color to this at the end, or to this side, which is the clear liquid with no color. So you see the difference? Please say you see the difference. Thank you. Because that is the evidence for the reaction. So that greenish color that we have around this electrode here, it shows that bromide has been oxidized, and it changed to bromine compound, bromine. Okay, this is the last experiment or the last reaction that we are going to test for the oxidation reduction in the electrolytic cell by using battery to generate or to supply electrical energy for our study of these reactions. And just make sure to look for all the choices. Do not write just it turned red or it turned yellow color. Please include, if the pink color appeared, what does it actually mean, and write the half reaction for each oxidation and reduction. Oxidation happens in anode, reduction happens in cathode. So make sure that you write the half reactions properly. Thank you.